Polar coordinates are part of exercise 15G. So we can usually express a point on a Cartesian plane, and we express a point by how far away it is from the origin in the horizontal direction, or your x-coordinate, and how far away the point is from the origin in the vertical direction, or our y-coordinate. But this is not the only way to describe the position of a point on the plane. Instead, we can use polar coordinates where we describe points by their direct distance, or r, from the origin, and also the angle that they make from the positive x-axis. Note that sometimes r will be negative, and I'll explain what this means a little later on. So instead of having x and y as a coordinate, I can represent a Cartesian coordinate in terms of polar coordinates, r, theta. An example of this might be the point 1, 1. This is its Cartesian coordinates. But I can also write this point in terms of its polar coordinates. So first, let's look at the direct distance of 1, 1 from the origin. I can do this using Pythagoras. So I know that r will be the square root of 1 squared plus 1 squared by drawing in a right angled triangle, and that's just the square root of 2. I can also find the angle that this point is from the positive x-axis. If I go in an anti-clockwise direction, well, I know that for an isosceles right angled triangle with sides 1, 1, and hypotenuse root 2, the angle must be 45 degrees, or pi on 4. So I know my point 1, 1. I could express this as r is root 2 and theta is pi on 4. That's its polar coordinates. Sometimes a polar plane can be used to depict where these polar coordinates lie, and it looks something like this, with degrees going around, or radians going around, and then also my length r, or my distance from the origin across. Let's start by converting Cartesian coordinates into polar coordinates, similar to what we just did. So if we have x, y, I want to convert that into r, theta. The main idea is to sketch and then use Pythagoras to find r, and use trig, most likely tan, to find theta. Generally, we do this in radians, so it might be useful to check your calculator setting is in radians as well. We'll go through 3 examples. If we have the Cartesian coordinates 3, 3, we need to convert this into r, theta. So the first thing we do is a brief sketch to figure out what quadrant this point is in. So I know r is this distance, and I know theta, I'm going to choose to go anti-clockwise from the x-axis. To find r, we are going to use Pythagoras theorem, just like we did in the previous coordinate point. Okay, so I'm going to draw the triangle here for the point 3, 3. So I'd have 3 along the base, 3 vertically up, and then I'm trying to find r, or the hypotenuse. By using Pythagoras, we'll have r equals the square root of 3 squared plus 3 squared, or r equals the square root of 18. If you simplify that, we get 3 root 2. So I found r, now I need to find theta. To find theta, I always just use tan. We know tan theta in our case will be positive 3 over positive 3 because I'm in that first quadrant. Simplifying the right-hand side, I get tan theta equals 1. And we know, either using your general knowledge or your identity triangle, that theta must be pi on 4 for tan theta to equal 1 in the first quadrant. Three in polar coordinates is equal to 3 root 2. That's the direct distance from the origin, and my angle is pi on 4. And as you can see in that diagram, I have a diagram of my point on the polar coordinate plane. Last example here. We're going to look at the point 2, comma, minus 2 root 2. So on my Cartesian plane, let's have a look. I'm going to be in quadrant 4, right here. This is the point 2 minus 2 root 2, approximately. So we start as usual. This time I'm going to draw a triangle. So I know that R can be found using Pythagoras. And I'm just going to draw the triangle in here for clarity. I'm going to include the fact that my y-axis is negative. In this case, I'll have that r equals the square root of 2 squared minus 2 root 2 all squared. Or when I simplify that, I get r is equal to 2 root 3. Right, perfect. Now to find theta. Again, we're going to use tan. Remember that's opposite over adjacent. And we're going to keep the negatives in that triangle because that's going to give us the correct outcome for tan. So I have minus 2 root 2 as my opposite. My adjacent is 2. So minus 2 root 2 all over 2. Simplify it, I get tan theta equals minus root 2. Now, I'm not sure what this is. So generally, if you're not sure what this is, you can probably use your calculator. Just make sure in radians. Take the inverse of both sides because we know theta is going to be acute, right? It's going down and it's just in that Q4. So I can solve for theta on my calculator. I will get theta equals tan inverse of minus root 2. And then I will find that theta is approximately equal to minus 0.955 radians. So from 2 comma minus 2 root 2, we get that r theta is equal to 2 root 3 comma minus 0.955 radians. I'm going to take you through the next examples in a second video.